So given a Hamiltonian system, right, it would be desirable if the modified vector field associated with a numerical method is also Hamiltonian. It's also Hamiltonian with some modified Hamiltonian function. Okay. So it turns out that when you apply symplectic integrators to a Hamiltonian system, it's like then the modified equation associated with the symplectic integrator is going to again be Hamiltonian. Okay, so symplectic methods give rise to modified equations that are Hamiltonian. With the following property. Okay, so in particular, the first thing is that the modified Hamiltonian let's call that h tilde as a function of h is close to the original Hamiltonian. Which is to say that h tilde evaluated as z, it's a function of h minus hz in some norm is big O of h to the p, okay, where p greater than or equal to 1 is the order of the method. Right, and the second thing is that f tilde, which is of course the modified vector field of z and h, is the sort of Hamiltonian vector field associated with some modified Hamiltonian h. Okay. So I should be cautious by saying that, you know, in general, it's like this h tilde is not going to be the thing you get where you take the limit as I goes to infinity. It's like of this, you know, asymptotic expansion, there's going to be some sort of truncation, and it's not going to be the case that the you know, the symplectic integrator applied to the original Hamiltonian system is exactly the time h flow of this modified vector field, but it's very, very close. Okay, so the error will be very small, but it will not be zero in general. Okay, all right. So thus, a symplectic integrator solves a slightly modified or perturbed Hamiltonian system. Exactly, in some sense, not again with that caveat about the errors being small, but not really zero. Okay, so if the qualitative solution behavior of the given problem is stable, under small perturbations. So as an example, if there was some sort of Km type theorem which applies in this problem, then the symplectic integrator will reproduce this qualitative behavior. So in fact, it's what, in some sense, one of the messages, if you will, of backward error analysis is that in general, of course, when you apply a discretization, you can think of it as a perturbation of the original dynamical system. So the kind of things you expect to be able to extract from a long time numerical solution are things which have to be, in some sense, structurally stable, which is to say that these are qualitative properties which are somehow robust to small perturbations in the dynamical system. And so you might ask, well, what is the value then in using geometric integrators? And I guess one way to sort of think about this is that when you have a geometric integrator, the perturbations, it's like to the equation you have are in some sense more structured. They're sort of a smaller class of perturbations. They're not as generic. And the hope then is that because you are perturbing that original dynamical system with a smaller class of perturbations, then the class of things which are in some sense structurally stable with respect to that class of perturbations will be larger. Okay, so that's sort of one argument, if you will, it's like to be made for using geometric integrators, is the hope that the class of qualitative properties which are structurally stable under a more constrained set of perturbations is larger. Okay, so all right, so let's see examples of this. All right. Okay, so for example, a non-Hamiltonian perturbation right may change stable centers into sort of sources and sinks, right? So the fact that you have a Hamiltonian perturbation, it's helpful because it's again a more restrictive class of perturbations to the dynamical system. All right. So anyhow, so let's look at some examples of this. So let's consider the explicit Euler method and symplectic Euler, or symplectic Euler A methods applied to Hamilton's equations. Okay, so if you recall, Hamilton's equation says that Q dot is equal to M inverse P, and then P dot is equal to the negative gradient of the potential at Q. So this is sort of a mechanical system. So this is Hamilton's equations for the Hamiltonian given by let's see, 1/2 P inverse, well, P transpose M inverse P, right, plus V of Q, right? So it's just a kinetic energy and potential energy separable Hamiltonian. Okay, so if you have this, then explicit Euler sort of gives first order modification to the vector field. which looks like delta F1 Q of P is equal to negative 1/2 F prime of QP F of QP, right? So this is what we had obtained before, right? That's the first order correction. It's like from Ford Euler, and we can write down what that looks like. That's negative 1/2 0 M inverse minus the Hessian of the potential 0 multiplied into M inverse P and the negative of gradient of the potential at Q. Okay, so that looks like 1/2 M inverse gradient of the potential and the Hessian of the potential multiplied by M inverse P. Okay, so you can observe that this vector field is not conservative. So this vector field is not conservative. So what that tells you is that it cannot come from, it's not a Hamiltonian vector field. So okay, all right. So this is just an example. If you applied explicit Euler to Hamilton's equations, then the first order modification of Hamilton's equations gives you a correction factor which is not itself Hamiltonian. Okay, it's not so surprising. The explicit Euler method doesn't preserve any structure which is relevant to Hamilton's equations. You don't expect it. You don't expect that the modified equations respect that Hamiltonian structure. So let's see what happens if you used a symplectic Euler A instead. Okay. So if you had symplectic Euler A, okay, then it says that Qn plus 1 is equal to Qn plus H M inverse Pn, and Pn plus 1 is equal to Pn minus H gradient of the potential evaluated at Qn plus 1. Okay, so the main distinction again is that the sort of the force, it's like due to the potential, is evaluated at the end, sort of the right endpoint instead of the left endpoint. And then if you Taylor expand the second equation, right, you get that this looks like Pn minus H gradient of the potential at Qn minus H squared, the Hessian of V M inverse Pn plus something which is big O of H cubed. Okay. So if you compare this with the Taylor expansion at the exact time H flow, right? So comparing with the Taylor expansion of the time H flow of the modified vector field, right, we obtain sort of a first order modification which looks like the following, which looks like delta F1 QP is equal to 1/2 M inverse the gradient of the potential and negative the Hessian, well, yeah, negative the Hessian potential applied to M inverse of P. All right. So the main thing is that there's a minus sign here where there wasn't a minus sign here. Okay. So the net effect of that minus sign is that now that vector field is conservative and comes from a Hamiltonian. Okay. So this term is conservative. can be written as the following, right? Delta F1 QP is equal to, right, the gradient respect to P of delta H1 QP and minus the gradient respect to Q of delta H1 respect to QP. So this is basically saying that this is the Hamiltonian vector field associated with, so this is the Hamiltonian vector field associated with delta H1, if you will. Okay, where delta H1 is equal to, which is a function of Q and P, is equal to 1/2 P transpose M inverse, the gradient of the potential. Okay, so therefore, symplectic Euler A is a second order integrator for a modified Hamiltonian system with a Hamiltonian given by, with a modified Hamiltonian given by H tilde 1 of H is 1/2 P transpose M inverse P, right, which is plus V of Q. This is, of course, just the original Hamiltonian plus the correction factor, which is H over 2 P transpose M inverse the gradient respect to Q of the potential. All right. So yeah, so that's kind of interesting. And then we'll show sort of more systematically that anytime you apply a symplectic integrator to a Hamiltonian system, you will have the property that the correction terms in the modified equation, it's like, can be viewed as Hamiltonian vector fields of modified Hamiltonians. All right. So let me just stop here for now.